Here are solutions to homework set number 13 for ECE 463-663 Modern Control. This homework set looks at LQG-LTR methods. So the first problem is given a cart and pendulum system, something that we've looked at before. Come up with a feedback controller to make it behave like a reference model. And here defining it to be 1 over s squared plus s plus 1. With LQG-LTR, the idea is to form a reference model. This is this guy right here. That tells you how the plant should behave. I'll then take the plant's response, compare the actual output to the model's output, call that the error, come up with the full state feedback gains, kx for the reference model, kx for the plant. Pick these so that you minimize the error, the output y right here, while minimizing the input. So the first step is to form the augmented system. So here's the plant, the reference model. The error, this is the output of the system, is y minus y model. In MATLAB, I can do that. So use your MATLAB code. I define the plant dynamics, the reference model dynamics, form the augmented system, make the output the difference between the two outputs. Then my Q matrix is just E squared, C transpose C, and R is 1. I'm going to look at how it behaves when I have the weighting on Q being 1,000, or 100, 1,000, and 10,000. So let's start out with 100. So there's my feedback gain K6. The first 4 gains are Kx. The last 2 are Km. Then simulate the system. There's my step response. Here's my feedback. Gain times the model. Gain times the plant. Given the input, feed it into the plant dynamics. Given the reference, feed it into the reference model. Integrate, move forward in time. Okay. To see how it looks, what it's doing, let's take this, slide it over. So when I run it with a gain of 100, the pink is the reference model, the red is the plant. So here you can see it's not tracking real well. That's with a weighting of 100. Well, with LQG-LTR, as I crank up the gain on Q, I get better and better responses. So making the weighting on Q 1,000. Again, now it's tracking better. Still a DC gain. That's the property of LQG-LTR. It's a trade-off of the input versus tracking error. I can tolerate a little bit of tracking error if it reduces the input. And with 10,000, it gets better and better. So that was the first 2 problems. Now there's a variant on LQG-LTR and your step response. The variant is, if you want to get rid of the steady state error, I can add an integrator. What that does is at steady state, z equals 0, meaning z dot e, or z is a constant, meaning that e equals 0. By adding the integrator, I force the steady state error to 0. Now do the same thing. I am going to use LQR techniques to find the output to be z in this case. That's kind of a quirk of Servo Compensators. The weighting is actually on the state you don't care about, z, and ignore the state that you do care about, E. Basically, the math is dumb. It thinks this is the output, Y, and it thinks this is Y dot. So by weighting the error, I'm actually weighting Y dot, meaning get there slowly. By weighting Z, it says get there quickly, so to steady state. But anyway, we'll get to that in a sec. So here's the augmented system, the plant, reference model, servo compensator. Putting that in state space, here's my plant, servo compensator, reference model, the dynamics, the A matrix, B matrix, B with respect to R, B with respect to U. Here's my input. When I find my full state feedback gains, that'll be Kx, Kz, Km. Now in MATLAB, I can find it. Kind of the same procedure as before. I define the plant, the reference model, from the augmented system, that's your A7, this guy right here. B7 with respect to U, B7 with respect to R. Your C7, I'm looking at the servo state. Q is C transpose C, and change the weightings. So let's start out with a weighting of 100. So if I weight the servo state with a weighting of 100, there's the plant in the reference model. Note by adding the servo compensator, the steady state error has to be 0, or DC gain has to be 0. It's going to track at DC. During the transient, the tracking isn't great. That's with a weighting of 100. Increase the weighting to 1000, right here. It'll track better. And the tracking will not be perfect. I'm trying to force a fourth order system to behave like a second order system. Actually, fifth order system when you add the servo compensator. It'll never be exactly the same. In addition, I've got this little wiggle right here. That's a property of the plant. In order to get it to go left, I have to first go right, get the pendulum to start leaning. Then I can come over and catch it. And you'll see that right here. It'll first go right, then left. Plant goes right, then left, gets it to start leading, then catches it. But as you crank up the gain, the response gets better and better. I could actually do better. If I come up with a better reference model that more represents the dynamics of the plant, such as a fifth order system, it'll work better. But I kind of find this neat about LQG LTR. Define the reference model, and you're forcing the plant to follow the reference model. So likewise, if it's not that hard then to specify the settling time, the overshoot, that's all defined by the reference model. And then the feedback controllers try to make the two behave the same. But that's homework set number 13 for ECE 463, Modern Control.